Let's start by deriving the equations of motion for a mass spring damper model, an example of a dynamic system that evolves in time. Deriving the equations of motion for this model is usually done by summing the forces on the mass, including any applied external forces. These forces include the force applied by the spring proportional to displacement and the force applied by the damper proportional to velocity. By rearranging this equation, we can derive the standard form of a second-order dynamic system. Typically written using the natural frequency and the damping ratio, constants derived from the study of vibration of mechanical systems. This is also an example of a linear time invariant system, a system that produces an output signal from any input signal subject to the constraints of linearity and time invariance. These systems can generally be written as a linear constant coefficients differential equation. Using our famous integral transform, which works very well with such differential equations, and assuming null initial conditions, we can construct the zero-state response of the system. The zero-state response can simply be written as a convolution between the impulse response of the system and any forced input. But the internal stability of the system is determined by the zero input response. Even when the input is zero, we find that the system has a response due to non-initial conditions. This zero input response can generally be written as a sum of complex exponential functions, with the coefficients of the exponents determined by the roots of the characteristic equation of the system. The roots of the characteristic equation are called the poles of the transform of the impulse response of the system, the transfer function in the frequency domain, which models the system's output for each possible input. Analyzing second-order systems in specific is of great importance, since a lot of higher-order systems can be approximated as a second-order system. This system has two complex poles, which can be written in terms of the natural frequency omega n and the damping ratio zeta. These two roots can be plotted on a complex plane, using constant values of zeta and omega n. The position of these roots on the complex frequency plane determines the stability of the system. Notably the real parts of the roots, since these correspond to real exponential components. For a linear time invariant system to be stable, the zero input response of the system, which is influenced by the initial conditions, has to decay as time approaches infinity, which allows the output to eventually approach the input in the steady state after some transient period. A single root positioned on the left-hand side of the real axis corresponds to a decaying exponential. If the root is zero, it corresponds to a constant response. When the real root is positive, this corresponds to an unstable increasing exponential. Assuming real coefficients of the characteristic polynomial of the system, imaginary components only appear in a pair of complex conjugate poles. And these imaginary values correspond to sinusoidal oscillatory components. We can then divide the complex plane into three regions. The open left half of the complex plane, where the real part of the roots is negative, is a region of stable response. The y-axis, where the real part is zero, is a region of margin stability. And finally, the open right half of the plane with positive real parts is a region of unstable response. A typical feedback control system can be modeled using a block diagram, with two transfer functions, in forward and feedback roots. We can then derive the closed-loop transfer function, describing the net result of the effects of the feedback control loop on the input signal. We can get the characteristic equation of the system by equating the denominator with zero. In systems without pure delay, the product g of s and h of s is a rational polynomial function, which includes a system parameter or gain k. Varying values of the parameter, k, change the pole locations of the closed-loop transfer function. At k equals 0, the closed-loop poles equal the open-loop poles of the function g h, and as k goes to infinity, the closed-loop poles either equal the open-loop zeros of the function g h, or the poles themselves approach infinity. The characteristic equation gives us two important conditions that allow us to compute the value of k at any closed-loop pole, known as the magnitude and angle conditions. To make things clear, let's say we have the characteristic equation of a fourth-order closed-loop feedback system. At k equals 0, the solutions of the characteristic equation are the open-loop poles of g times h. Notice that the open-loop transfer function only has 3 zeros. As k increases, the solutions of s to the characteristic equation traverse a curve known as the root locus of the closed-loop transfer function. Root locus analysis is a pivotal technique in control theory used to determine the stability and response of dynamical systems. The stability of dynamical systems ensures that systems behave predictably and safely, even in the face of disturbances and uncertainties. Root locus analysis provides a graphical method to visualize and address these stability concerns, making it an indispensable technique in the field of control engineering.